In mind from the previous lecture is that DNA is a flexible continuous polymer, but without any temperature it should be a straight line because you have a Young modulus. But because you are in solution and then you have the solvent molecules that will come, you will have some deformation. And for sure, further you go along the chain, the more the influence of the shocks will be. And so it means that if you have a given orientation on your molecule at one hand, after some distance you are going to lose the orientation that you have given. And the typical distance where you lose the orientation is the Besson length that is indeed related to the Young's modulus. And this is what we have seen last time. So the point is that then the final configuration of the chain is a random coil, and I think this is something that I didn't write and I should have done. So the chain can take many configurations, and when you apply a force, you reduce the number of configurations. And to do that, well, you need to have a mechanical action on your polymer. So we did solve the case where the chain was considered as a very simple random walk. The case where you have, I think I will switch that part. The case where you have the flexible polymer is a bit more difficult to treat. So because the energy is given by the local curvatures that you may have, so you will have the elastic cost of bending your chain, and since you apply a force, you also have the mechanical term that goes into the energy. So, in principle, you should write the partition function of such a system, then you get the free energy, and in the end, you may get the force versus extension relation. So this is not that simple, so but the problem was solved almost 20 years ago by Jean-François and Eric Sijam. They have demonstrated that the system describes very well the DNA elasticity. So this is a curve that I did present you during my first lecture. So it should be this one. So the one action curve is the blue one. The experimental points are here, are very well described by this curve. So they gave, so you don't have any analytical solution, but they gave this approximation. So you have the three terms that they proposed. But in fact, the precision of the experiment is good enough so that it's better, if you want to get a precise measurement of your experiment, it's better to add some additional terms, and the terms are given by an expansion with different values that you have here. And this is just for people who are interested in getting precise measurement on polymer elasticity when you are putting on a single polymer. So, now we're able to describe the elasticity of a single chain. So we know, we know what's happening when we pull on the chain. So here we don't have the Gaudian motion. Okay, if someone wants to come. But no, you keep it. Now there is something special with it. What's the difference between DNA and another polymer? What is made DNA of? What's its structure? It's a double strand. Usually, most of the polymers that you use are single strand. So, usually, most of the chemical bonds, you have almost a free rotation around polymerized. Now, we have a double strand, and so what is going to happen is that we do also have some elastic properties, but now in torsion. Okay? Keep it. So, you see now, we see some ondulations. I'm going to increase a little bit. A bit more. Is it okay for you? Yeah. Maybe you can go in the opposite sense, so we are going to get some more. So we are going to make it shorter. Okay, we take a smaller one. Okay. Which way are we doing? Okay. Okay, so now we see some ondulation, but it's not that impressive because we are stretching. Now, if I reduce the force, you see what's happening. You have some coils that appears. Okay? Those coils, I'm going to call them plectronins later. Okay? So now you have to give your impression to the room. Okay? Now, is it difficult to maintain the elastic, the rubber torsionally constraint? Is it?
Yeah.
Is it more difficult or compare this to that?
The one we use first is more difficult.
This is more difficult. Okay? So, in physical terms, how would you say that what is mechanical action that you have to apply that is stronger, more intense in this position, less intense in this position compared to that one? What is mechanical action? The question is for everyone.
The preferred state is the coil.
So, if you want to rotate something, what is mechanical action that you apply? Mechanical action that you apply? Twist the torque. Yeah. So, when you apply a torque, when you rotate your polymer, you see that you may have structures that appears like this, or that may disappear. This depends on the force. But there is another action, that is that the torque that you have to apply on the extremities to maintain the number of turns depends also on the force. Okay? And so this is one peculiar aspect of DNA elasticity. So we need to describe the system. So as we said, DNA is double helix, and so it has a given number of turns. So, as I said during the first lecture, in the standard, what you have in solution in DNA structure, you have 10.5 bases per turn. It means that if you have a long DNA molecule, the initial structure where the DNA is in fact relaxed, torsionally relaxed, you have a number of turns. Maybe I wrote it here. No, yeah, I wrote it here. You already have a given number of turns of one strand around the other. That's given by the number of bases divided by 10.5. And what we are going to do, what we did when we rotate the extremity of the DNA, is that we change the number of turns one strand is making around the other. To remove this number of turns, so we could stretch the polymer, to hold it in the correct way, we can stretch or not, the number of turns is always here, okay? So the torsion seems to take two possible forms, that could be visible. But in any case, if I want to remove all the supercoils that I have here, I must rotate, and the number of turns that I have to rotate is exactly the same as the one that we initially have to have. Okay. So we have some kind of invariant, and this invariant is called LK, the linking number. And this is simply the number of turns one strand is making around the other. And depending on the force, as we have seen, it may take two forms. One is simply the twist. And this will take the angle that takes the helix that you have to integrate all along the chain. Or it can take the structure on the right, and one aspect is how the plectronins. And if you want a mathematical formula for that, you have this formula, and as you see, it's a non-local integral that you have to make on your polymer. So usually it's not that fancy to calculate, but it's something that we have to deal with. So depending on the force, when you constrain the linking number by rotating the extremities of your polymer, depending on the force, you may have more twist, so the torque will be bigger, or you may have some rise, and then you will have the plate cloning structure that will appear. Okay. Okay. So the topological constraints that we impose can take two forms. And in fact, what is interesting to compare different DNAs of different extensions is not simply the linking number. This is the density of supercoiling, that is the difference between the linking numbers that you have at a given time minus the natural linking number of the DNA molecule, which in our system will be related to the 10.5 basis pattern, divided by this number. And so by using this quantity, you can compare different molecules of different extension, because for sure, if you have a long molecule that you make one turn, it will be a small disturbance, whereas if you have a very small one, it may have a large effect. Okay?
Excuse me, Jean-François, I'm worried about the denominator in that equation, because, no, on bottom. Because what happens in the case of a molecule that's not helical, so just your row, if there's no natural twist, isn't the LK0 equal to 0? No, because of course you will diverge, so you will have to find another normalization constant. So if you do that, if you have a polymer that does like that, you should at some point divide by something that is related to the extension of your polymer. So would that be the case for your rope, for example, for this illustration? Does that have LK0 equals 0?
I don't know, but maybe. But when you hold the two extremities, if we say that it's something that is equal to 0, you can do this, and then we have a linking number between the two spheres. And you see, we do form pectinins that have a more complicated structure, but it's possible to do that. So it's simply that you have to normalize something, compare polymers of different extension, because you will have a relative effect, okay? And so this is to take that into account. But it's true that if you take exactly the same definition for a polymer that is but in fact, you are not considering one polymer, then you are considering the braiding of two strings, which is slightly different. So you should take another normalization constant. Okay. So, a DNA molecule is a helix, so it has some chirality. Okay, so you may add some terms in the same direction as you have the natural helical pitch, okay? Or you may go in the opposite direction. Okay? So you may give a sign to LK that could be positive or negative depending if you add terms or if you remove them. And depending on the sign that you have, maybe I'm going to take this example because here you have a circular polymer and here you have a linear one. So if you rotate in one direction and you take a given sign, it will be -1, so you may have the twist. Or when you look at the crossing here, so you may have then the rise, the crossing, you have this strand that goes above and it comes back below. If you give it a rotation in the opposite direction, you see that you go below and then you go above. Okay? So you have the sign that is represented in the twist that is also present in the right. Okay? And you see that if you have two turns, well, you have the same thing. You may have a partition where you have simply one twist and two right. But these are examples where you have something that is discrete, but you may also have some real values. Okay, so you can play with that. To generate some supercoiling on a polymer, as we have seen, because we did the experiment here, you need to hold the two extremities and to constrain them. Okay? So it means that in real life, to produce some torsion on DNA, you will need to have DNA that will bind to some specific structure inside the cell at different points. Or, what people usually do, because it's easier, you take DNA molecules that are circular, that are called plasmids, and so then you can play quite more easily because you don't have to mechanically constrain the extremities. Okay? So in most biochemistry experiments using topology of DNA and supercoiling, they do experiments on circular DNA, whereas the techniques that I'm going to present, I hope today, we can work on linear DNA. Okay? The question is that, do you have any idea whether this is relevant in vivo or not? So the clickers say yes, at least for places. So why?
I just know about supercoiling, about the phenomena.
You know that it exists. Okay.
Doesn't it have to do with the switch, with the, amongst other things, epigenetics, where by supercoiling you don't get access to the machinery to the DNA? The
Yeah.
enzymes?
Okay, there is some epigenetics, but it's not directly related. Okay. But it's an important process, and I will discuss that not today, but on Friday. How do you compact? So we said that you have something like a meter of DNA into your cells. Okay. How do you compact the DNA into the nucleus of your cells?
Tightly.
Yeah, you have to compact it tightly. Do you think that DNA is free inside the cell, or there are some proteins?
These cells.
There are proteins, and do you know to what are the proteins that you have in your cells that helps to compact the DNA?
These stones.
These stones. And what is for a physicist? So it would not be a spherical cow, but something like that. What is an histone for you?
Yeah, it just helps, as I understand it, helps to order the DNA so that, helps order the DNA so that the enzymes can get to the DNA, doesn't it?
It holds the DNA, so in fact it's a small barrel, okay? So on every stone you can make 2 turns.
Okay.
I will need your help. So you hold the tube here, I'm making 2 turns, okay? I'm not placing any rotation, I'm not adding some rotations. I do the same thing, I put 2, I hope I won't hurt you, 2 other turns, okay, to amplify the system. And now we remove these stones. So we can take the stick up, the stick. Oops. And now you see that you have the supercoiling. Okay? So inside your cells, you have proteins, and DNA is wrapping around those proteins. So they are called the histones. So they are small barrels. And those histones, when you remove them, you see that you can see platonins. So the coiling around the histone is a way to introduce some supercoiling in the DNA. Okay? So this presenting you, and if you isolate some DNA from a bacteria, for example, you see that it's naturally negatively supercoiled. Okay? DNA is supercoiled inside the living cell.
That was my question. Because most of this the examples you give us, we see the DNA which is negatively supercoiled.
Oh, here it's negative, here it's positive. I'm sorry for the definition of the image, but here it's negative, and here the example it's negative and
yeah, but why in organism most of DNA is...
Well, there is symmetry breaking. So we have an expert of symmetry breaking here. So why do you have symmetry breaking in line?
Well, it's not symmetry breaking, right? Because it's
DNA
either reducing the natural cloning or increasing the natural.
Yeah, but DNA is naturally asymmetric too. So there is a symmetry that was broken already. But you may say also that you know the amino acids, they have a preferential symmetry also. It's levogir and dextrogir, okay? These are the English terms. Chirality, yeah, you have some chirality, and you have that also. But I'm going back to what's interesting in the living system, to have some preferentially negatively supercoiled DNA. So now, as a physicist, you say, okay, I have a semi-flexible polymer, so I have to put some energy to bend it. I will do an experiment when I'm going to stretch it. And I know that I have some torsional constraint to apply on my system, and so there will be a kind of torsional modulus that I have to take into account. So you see the energy is something like a constant times an angle to the square. So this is a traditional way of having some torsional energy. So you see appearing here a quantity C that is in fact similar to what you have here for sine, that corresponds to a distance over which you lose the correlation in angular orientation along your molecule. So if I hold one extremity here, I have some body on motion, so I will have a little bit of rotation, and after some distance, typically C, I will lose the initial orientation that I have for my polymer. Okay? And this is a way to put the energy and to use this term. Okay, so this is the energy, and in principle you should simply have to put this into a partition function and to calculate. So the initial point, as I said, was solved only 20 years ago, and the full one here is not solved completely, even though there are quite conclusive results. So the experiment when you use a DNA molecule, if you take this rubber tube, okay, I expect to have, if I don't move strongly, to have, I will need your help again. Okay, so we have the supercoils. I went in this direction, now we are going into the other one. And we do have the same. And this is symmetrical. Okay, if you take a rubber tube, you expect that when you rotate your system, you will have something that is symmetric. And so here, initially you pull your polymer described by the Wernher chain, you start to rotate, and at some point you generate some supercoils. And when you have the supercoils that are generated, if I want to increase this, if I increase the number of turns, I simply increase the size of the supercoils, okay? And when I do that, for sure the length that I initially had in this direction will go into the supercoil and will not participate to the end-to-end distance. So when the supercoil forms, we have an increase in extension. Okay? The nice point is that this curve, as you can see more clearly here, is linear. And the slopes correspond to, in usual condition, at around 40 nanometers per turn. Okay? So each time you add one term on your polymer, for the DNA molecule, you have a decrease in extension of about 40 nanometers. And this is interesting because it's possible to use this to study enzymes that do modify the torsion of the DNA. So now this is what is occurring at low force, 0.2 piconewton. I'm going back to the units and the order of magnitude of those force later. Now, if we increase the force slightly at about 1 piconewton, now we see the chirality of the DNA. DNA decrease in extension here, so it's similar to here, so we expect that we do form leptonins, but on this side, we do not form leptonins anymore. So, the small figure here gives you an idea about what's happening. Inside the DNA molecule, you have some hydrogen bonds. Okay? When you untwist so we have, can you hold the two? This represents the two strands of the DNA molecule. We have initially a pDNA molecule, so it's twisted. We unwind it, and then we tend to separate the strands. Okay? This is quite natural. So what's happening is that here, when you go in this direction, you increase the torque that is inside the molecule. So when you go there, you increase the torque. But the torque depends on the force, as we said. And here we're at a force where the torque is high enough so that you can break, at least locally, the hydrogen bonds. Okay? So here you have a region where DNA is in nature. Denaturation. So you break the hydrogen bonds. Or you locally melt the DNA. Do you see interest in that?
So for the largest force in blue,
Yeah.
you didn't want to give us the whole picture, or because I think you should have where you have the zero extension. For
What? Here?
Yeah.
It's
Is it plateau that way?
so here it's 200. So this experiment was done on a lambda molecule. A lambda molecule has 50,000 bases, so it means that it has 5,000 turns, about 5,000 turns. Okay, so if I want to see where this curve is going to zero, the intersection should be at minus 15,000, plus 15,000. Okay? So it's very, very far. So this is why here we stay in a region that is quite reasonable. And this is where the living system is working. And typically for in vivo, what you have is lying here. Okay? So we said that when we go into the opposite direction, when we try to unwind the DNA and we pull slightly on it, we have some denaturation bubble, and so we have bases that are exposed to solution. So Michel Wang in experiment recently, they say, well, this is not simply the denaturation bubble like that, but it's like it should be a left-handed structure, but it's an element, but not critical for what we want to say. So you see now, you stretch, you rotate, you have access to the sequence. In DNA, the sequence, the genetic code is inside, okay? Here you have mechanical access to the inside of the system. Usually the bases are protected, okay, in the B form of DNA. Now, if you play with the mechanics, you are able to have access to the bases and then to the genetic code. And in fact, enzymes that need to read the genetic code, most of them, they open the double helix. And if you initially in your system, you are already there, okay, it means that it's easier to have access to the genetic code. So by controlling the supercoiling, you can in a sense control the access to the genetic code. And so this is why it's important. So as I said, most of the living systems, you are negatively supercoiled. In fact, you have few species where DNA is naturally positively supercoiled. And those species, they do live at high temperature. And you see the problem that you have at high temperature is that DNA, at least at the pressure that we know, the DNA melts at something that is about, usually what you use in PCR is something 90 degrees or 94 degrees Celsius. Okay, so usually if you put two pieces of DNA at 90 degrees, they separate, you break hydrogen bonds. So if you have an organism that lives at high temperature, its DNA will not be stable. So a way to have something that is more stable is to overwind the DNA in order to have a better stability when the DNA strands want to separate. Okay? So for this reason, in living systems, you have a negatively supercoiled DNA. So this answers to your first question. Yeah, so here you see we have with the bDNA form, and here we change locally, we have another phase where we have denatured DNA. So the behavior that we have here at a higher force, so here the force is 8 piconewtons, is slightly the same. Here we had something that is relatively flat, so if you go further you will have a slope for sure, but here it's flat. Here we have something flat, so we have exactly the same phenomenon. And here at high force we also have something that is flat. And the idea there is that you have also a new structure of DNA that appears. So the question is, what is this structure? And so when we found this structure, we were a bit in trouble, because usually to study the structure of biomolecules, we use crystallography, we may use some NMR. But the problem that we have is that to produce this structure, we need to have mechanical force on our system. So we should do some crystallography on systems where we are able to induce this structure only on few molecules, and we must have big objects close to the DNA. So it's not possible. So then the only solution that you have is to do some numerical simulations. Okay? And so people doing numerical modeling, they came out with a structure where you have usually you have sugar phosphate backbones that are outside and the bases that are inside. And so in the new structure, what's happening is you have the opposite. The bases are outside and you have the sugar phosphate backbone inside. So the problem that you have when you want to put more terms on something is that you want to have more terms. I mean, you rotate, my arm corresponds to the bases, okay? So I can make, with a given length, I can make only a few terms, okay? If I was a rugby player from South Africa, I could make only less terms, okay? And if I was a kid, I could make more terms. So if you have to wrap around something, you make more terms with a given length, is what is inside is smaller, okay? So here, the best way, since what is inside are the bases, the best way is to eject the bases outside, okay? So this is what the model is telling, and then you have to check this, and so we could check that the released bases were exposed outside, and we could do some chemical modification of the bases and detect the ones that were outside, and so this seems to be the correct structure of DNA that appears. So I'm going to show you further a picture, but you see that with a mechanical action, you can induce phase transition inside a DNA molecule. And those phase transitions may have some relevance for the biological activity of the molecule. Okay? So you have an interplay between the mechanical properties and the biological activity. And this is at the center of what we are doing. If you want to have some mechanical aspect view on this problem, at least at low force, you notice that here it's difficult, but here you see it more nicely. You see that initially, before you have the platonym that forms, you need to put some rotation. You need to add some terms to your DNA molecule. And here you have some threshold where you start to form the platonym. So at some point you have an instability, you have buckling instability. Initially you rotate your rubber, you rotate, and almost nothing. And at some point you have a buckling instability. Okay? So when does the buckling occurs? The buckling occurs when you make one turn. The energy that you have if you have a torque gamma is gamma times the angle. Where does the energy flows to? We're assuming that the very first platonym is circle of size r. So you have an energy that is 1 divided by r squared times, this is integral, this is the term that we use, sum over s squared ds. And here, instead of having 1/2 of kb take this is named b in this equation. So we assume that we have a circular platonym, just a circle, so we have this energy that corresponds to the bending energy, and since we have a force that is stretching the molecule, if we form a circle, we need to shorten the molecule, so we have to fight against the force. Okay? And so we have a decrease in extension that corresponds to the length of the DNA that is coming into the circle, and you have to multiply the displacement by the force to get the energy. So if you minimize what you have here relative to R, you get to a threshold for the instability, a torque that goes like the square root of the force. So this is why here the buckling instability, here it should be lying here, it should be lying here, and so on and so on. The point where you start to buckle and create platelets is proportional to the square root of the force. So this is plotted on this curve where you have the buckling position as function of the force, and here it's fitted with the power 1/2 load. To have a mechanical point of view of the system, what you may think about is to see what's happening inside the system. You initially have no torque present onto your DNA molecule. Then you start to rotate. When you start to rotate, you will have a torque. The torque is the torsional constraint times the angle. So you have something that is linear with the number of turns. And at some point you are going to buckle, and then after the buckling the torque will remain constant. Okay? So mechanically you increase the torque when you rotate initially, and at some point you saturate and you form platelets, and then you are at a constant torque. Okay? So this picture is a bit more complicated because you also have some threshold for the denaturation of the generation of the other structures that I did present. So in addition to that, you will have a threshold. If this buckling instability is lower than the torque critical to denature of the DNA, you won't have the denaturation. And if the denaturation torque is smaller, then you will increase the torque and you will get the denaturation before you get to the buckling instability. And this is why you have something flat. Okay? So depending on the force, depending on the number of turns that you have, you may denature or not, you may have some buckling or not. And this is how we explain those curves. Okay? Yes?
I don't understand what you mean by, is the buckling point the point by which?
Where you start to form platelets. Initially you have something that is twisted, but you can see it almost. Okay?
Oh, so the point
at some point it buckles. What?
The point for where you have
so you have this phenomenon,
okay.
and then you have denaturation. Okay? So if the bending rigidity of this if I would like to put some supercoiling on this piece of wood, okay, in fact it would break before I could do any rotation creating a platelet. Okay? So this is what's happening when you denature the DNA. Yes?
Sorry, maybe I missed the detail, but so the chirality of amino acids is well understood how this affects the...
No. The amino acids, no, it's...
This is not well, it's not
yeah.
simply electrostatic or bond related.
No. This is very different. I simply wanted to mean that there was some symmetry breaking in nature. This is the only...
Is this something that's well understood or...
For the amino acids, no, there was many speculations. So some want to see the hand of God, some... there were recently hypotheses. Well, you see, hand of God has some asymmetry too. So maybe God is right-handed or left-handed. But no, for the moment it's not absolutely clear. Okay.
And at the threshold, is there a critical value for the R, the size of the mechanism? Or
so the size of the initial buckle, yeah, there will be, but this will depend. It will depend. I mean, it will depend on the polymer, and because you have a competition between two energies. You have the bending energies. Okay. When you have the platelets, then the DNA is bent. Okay. And so here, when you have platelets, you take pieces of DNA and you are bringing them close to the other. So you see that there the electrostatics may be important. Okay? And the other energy is the torsional energy. So you have the bending and the torsional. So you have a balance between the two, and what is important to get those curves is the ratio between the percent length between this parameter and that one. Okay? And by playing on the ratio, so and then, as I said, I mean here it's a bit more complicated because then the electrostatic may come into play further in this part of the curve. So how people did observe that you have some supercoiling? So initially there was electron microscopy images. So you see here a relaxed DNA, here with more and more torsional constraint, and so you see that this DNA is more compact. So supercoiling is indeed a way to compact a polymer. So traditional way of studying supercoiling is to run experiments on a circular DNA and to place it onto a gel, okay? And so you will, in a gel you will have small pores, and this will have some problems to get into the pores, so it will move slowly in electric field, and this one, as it is more compact, will go faster. And so when you migrate the DNA in this direction, the compact DNA that will be supercoiled will move faster than the other ones, and then you can separate the different topologies of your system. And you can indeed separate different topoisomers. Okay? This is a traditional way. The point is that, as I said, in living system it's very difficult to control the supercoiling of the system because in your cells, in bacteria, enzymes do the job. And they do not set the supercoiling where you want, but they set the supercoiling where the living system works. Okay? So you cannot play that much. So you may play on some chemicals to modify the system, but this is not very flexible. And so this is why the macro manipulation techniques are useful to study this system. Just to show you, because in those systems, I mean, the supercoiling is fixed, so you don't see how the plectonins are moving. Recently, a year or two ago, the group of Kesdeker in Delft made made an experiment where they did label the DNA, and as you can see, when you have a plectonin, if the DNA is homogeneously tagged, when you have a plectonin, you have a lot of DNA that is present, and you should see a white spot. And so you see that the spots, they diffuse. At some point, some may disappear, and you have another one that appears in other places. And so with this technique, you can see whether you have one plectonin that absorbs everything, whether you have many of them, how long it takes to diffuse, and you may also study what the effect of the electrostatic, for example, because you said that we may have some effect because when you form a plectonin, you bring some pieces of DNA close to the other, and so the repulsion might be important.
Could I ask, what was the DNA label?
Here they use some Phi3 label. They use a fluorophore.
Yeah, and the presence of the fluorophore, doesn't it influence the supercoiling as well?
It does not in the way that they test. They could get the same curves. They did the curve with almost the same DNA. I mean, they took the same sequence, with and without, and they could get exactly the same curves. Okay, up to some noise that is already present in any experiment. Okay. So it did not affect, but it's true that as you add something that could be charged or that could modify the rigidity, you may affect. So then you may play also the ratio of the modified bases that you have. But in fact, it did not affect the system, and so it's a way of seeing that those plectonins are in fact moving some piece of DNA to another one. And so it's a living, in a sense, system. Okay. Now, my timing is not good. I want to spend some time on techniques, so I won't go very far. We said that the forces that we need to take into account are on the order of piconewton. Usually it's not a unit that we know that much, okay? So we should get some order of magnitudes. So how to do that? Usually we have some order of magnitude for the energy and quite often number for the distance. And so simply for scaling approach, you see that the force is simply an energy divided by a distance. And so to see what are the relevant forces in a system, you simply have to divide the energy by the distance that are typical to what you're looking at. If we think about the enzymes that do work into your body, most of the time the energy comes from the hydrolysis of a molecule that is adenosine triphosphate, called ATP, and in the conditions that are in cells, the energy release is typically 20 kT. Okay? And the distance is only few nanometers. So, I hope that you know what is the value of kT in a living system. Joule, okay? So if we take, we have 20 kT, and we must divide this by 1 nanometer, 10 to the minus 9. Okay, so we have, this is going to be 40, and 21 by 10 minus 9. So it's going to be few tenths of piconewton. Okay? So if you want to study molecular motors, you should be able to apply forces that are in the range of few tenths of piconewtons. And this is what indeed people observe in experiments. Now the same question, what is the force to break a covalent bond? I want a force, not an energy. So for sure, the energy will be on the other. Well, this is where we have problems when we have chemists in the room. They don't have the good units. We want to break a single one. Okay, so then you have the Avogadro number that is a bit disturbing. Okay, we want to break a single one. But physicists may help you. What do you do when you have? I mean, when you make a covalent bond, basically you mix electrons that are there. And the energy of an electron around the nucleus, the order of electron, the order is the electron volt. So this is 10 to the minus 19. And so the size of a chemical bond is typically the angstrom. And so this is going to be 10 to the minus newtons. That is 10 to the 3 piconewtons. Okay? So well, here we are doing experiments on DNA. We don't want to break it, so we know that we need to have a tool that is not capable of having bigger forces, otherwise we would break it. Okay? Now maybe what is more relevant, because I didn't read the number on the other day, what is a typical force to stretch a polymer just like DNA? When you have a polymer, the energy is the only relevant energy that we use is kT. So distance. A polymer is characterized by the only distance that we talked about. I mean, we had two, but one is very typical for a polymer. This is the distance length. And so I said that for DNA, the distance is 50 nanometers. So the typical force to stretch a DNA molecule is equal to 4 minus 21 divided by 5 10 to the minus 8. So this is going to be 0.8 10 to the minus 13 newtons. So it's going to be about 0.1 piconewton. So this means that to significantly stretch a DNA molecule, meaning that getting out from the just perturbation regime, we need to apply, that is on the order of 1/10 of piconewton. Okay? As I said, on chemical polymers like PDMS, they have a presence length that is about 5 angstroms, which means that its presence length is 100 times smaller. It means that the force to stretch the PDMS is going to be 100 times bigger, it's going to be 10 piconewtons. So this is the counterintuitive aspect of the system that we discussed on the other day. The presence length is much smaller, so it's more locally flexible, but it's more difficult to stretch the polymer. Okay? And if you think about, this is because when we, it again quite quickly, we use the enlargement force and the parameters that we had are the force divided, multiplied by the typical size of the random walk, which is related to the percent length times divided by kT. Okay? This is how you can get the numbers that we're looking for. Okay? So we need tools to apply such forces. So some of them were already mentioned. So the simplest one is to deform a very flexible fiber. So people did use some optical fibers that they did chemically attacked in order to have very, very thin piece of fiber that was easily deformable. So very close to that you have the use of the AFM, atomic force microscope. We heard about the laser tweezers. So the principle being, or you have some small particle that has an index that is different from the surrounding, and so the photons, when they will get there because of the Descartes-Snell elements or because it will be diffracted, they will change the direction. If they change the direction, they will change the momentum, but because of the action-reaction principle, it means that it's going to apply a force on the bead, or as it was presented by Ivan yesterday, you may say that here you focus a laser, so you have a gradient of intensity of the electric field, and so any particle that has some polarizability will be attracted by the maximum of the field, and so the particles will be attracted to this position. So you can do funny things with those elements. So this is what people in Netherlands did. They used a laser that they focused at different places, and they could trap different beads that they could manipulate, position in different places. You may see that the triangle is because you see the Brownian motion, you see that some positions are not occupied, but you can really manipulate the matter very easily. So maybe it's an expensive Tetris, okay? This is funny, but in fact people could, I think the high score, not at the Tetris, okay? To trap beads, I think is around few hundreds, okay? You can manipulate the light in order to, from one laser or multiple lasers, you can have up to few hundred beads. And people do use that to position beads in space and to have some kind of macroscopic crystal, okay? So they do that. This is in 2D, but you may have also the third dimension that can be used, okay? So even though this is funny, in the end we want to measure small displacement. And so when you want to study molecular motors or DNA elasticity or other polymers like that, you cannot have that many beads working at the same time because you need a detection that is precise for all positions. This is the point with the new generation. As soon as there is a game that they know, You can do other stuff. Where is it? This one. This is an experiment that was done in the group of Steve Quake, but the very first experiment on that was done in Kazuhiko Kinoshita lab in Japan. So what they did is that you can position a bit in 3 dimensions. You can capture a DNA molecule in between. You can label the DNA molecule as we have seen with the experiment of Kessdecker. Okay? If you move usually in water, the polymer will relax very quickly, and what you will have is that you will, even though you will see the flows that will deform a bit your polymer, it will relax, and you will have, between 2 bits, you will have a filament of polymers that will follow the one action. What they did in the group of Kinoshita that they used, and in Steve Quake's lab, they used a solution where there was some other polymers that were increasing the viscosity. So the relaxation constant was much smaller, and so they could take a piece of DNA, they could move in the 3rd dimension, the other one, make a loop, going back and going through the loop and make a knot. Okay? So optical tweezers are very good tools to manipulate matter. Okay? You can have 1, 2, 3 hundreds of objects that you can trap. You can do funny things, but in those systems it's not always obvious to do quantitative measurement. Okay? So you have to take care between the two. It's difficult, very, very difficult to have quantitative measurement on more than 2 bits. Okay? And I think I will stop here because then I'm going to describe something else and it will take more time. So I will stop there. Okay?